Hello again, my dear students, and welcome to the second part with our optical fiber communication lecture. Let me start with sharing my presentation slides and continue our optical fiber communication. Okay, I believe now you can see my PowerPoint slides. Let's now open the pointer and continue. Okay, in the first part of the lecture, we have dealt with what's called the construction of an optical fiber. We have understand the difference between a core material and a cladding material, where a core material should have a higher refractive index with respect to a clad material in order to obtain or maintain what's called the total internal reflection. Then we have also make a link between the acceptance angle or the acceptance core and the total reflection angle, so that we can have what's called the numerical aperture, which is sine theta A, where theta A is the acceptance angle. And we found that this is equal root n1 square minus n2 square under root. Then we have studied different types of optical fiber. The step index optical fiber, where you have a n1 constant and n2 constant over the core and the cladding respectively. This version can be either on a multi-mode optical fiber or a single mode optical fiber. And we set this empirical formulas where you can calculate the number of modes in terms of a dummy variable called V, which is a function of the numerical aperture and also the radius and the wavelength. And then we transfer to what's called the graded index optical fiber, where the refractive index of the core material is a function of position or a function in radius. As you can see, this function can have different order, starting from a linear function where alpha equals to 1 to an infinity function to reach the step index case. Herein, we found that the total internal reflection can happen inside the core material. Not all the signal will reach to the core cladding interface due to the variation in the refractive index inside the core material, so that the total internal reflection occurs in the point at which the condition sine phi, or the total internal reflection angle, is equals to n2 over n1. Then we have also reached an empirical formula for the single mode optical fiber, where you can calculate the cutoff frequency, or I mean the frequency at which, the maximum frequency at which you can send a single mode optical fiber for it. This is a function of V, which is again a dummy variable, the radius, the refractive index of the core, and the numerical aperture. Now we will start dealing with the input-output relationship of an optical fiber. So I mean, in the first part, we were interested in the construction of the optical fiber, either step or graded, the core and the clay, the refractive index, the numerical aperture, the angle of incidence, or I mean the acceptance angle, all this stuff. Now we are dealing with what will be inserted as an input to the optical fiber and what should be the output. So generally speaking, when you start to transmit data, let's say the most easy example to transmit 1 and zeros as a pure digital input like this one over an optical fiber, what you will recognize that the output signal will be something like that. So if you first starts to compare between the input and the output, you will find that we have inside the optical fiber two main effects, let me say. The first effect is the energy transmitted. As you know, if we consider this axis as the power or the intensity axis, and this as the time axis, so the energy is mainly represented as the area under the curve, because energy equals to power times time. So the power or the area under this curve represents the energy. So if you compare the energy transmitted to the energy received, you will find that the energy received is less than the energy transmitted. And this what we call the term attenuation. So the first observed phenomena in an optical fiber is that what you will receive in terms of power or in terms of energy, I'm sorry, is not equal or is less than what you have transmit. And we call this attenuation. Of course, attenuation can be given either in a form of a ratio or in a log format so that it will be in dB. So why we have an attenuation? Why there is an attenuation inside an optical fiber? So first, we can consider the optical fiber as a low pass filter effect. So if you have the time response of an optical fiber and then you make a Fourier transform, you will find that the Fourier transform for the time response of an optical fiber is something like a low pass filter. This low pass filter has, as usual, a 3 dB bandwidth. So after this cutoff frequency, the input frequencies will be significantly attenuated. And before this signals pass, this is the pass band and this is the stop band for the optical fiber. So what is, or actually what are the sources for attenuation in optical fiber? Actually, we have a huge amount, maybe unlimited sources of attenuation. This slide can summarize these sources. Some of these sources will be demonstrated in more details during this lecture, and some of them will be just for your information. But let's first start to scan these sources of attenuation. So the first source is what's called absorption. As you know, if you maybe from your physics classes or from magnetism or whatever, that for any electromagnetic field radiation propagating in a medium, there is mainly three sources or three probabilities that can happen. So let me go to my whiteboard for a while. Okay, perfect. Okay, so if this is a medium and you have a light propagating here, this light may be transmitted to the other side, reflected back, or absorbed in the medium. The source of absorption is to have this epsilon r equals to epsilon dash minus j epsilon double dash. Whenever you have this epsilon double dash effect, you have an absorption effect, or what you call in your microwave and EM course, EM2 exactly, what you call the losses. Whenever you have this epsilon dash, you have losses. Herein, we call these losses the absorption phenomena. As I mentioned in my first part, the root of this relative the root of this relative permittivity is the refractive index. So generally, you can say that n, which is refractive index, is equals to n real or n dash or whatever minus jk, and this k is of course corresponding to epsilon double dash is the term responsible for absorption. So absorption can occur in an optical fiber. But maybe the question is, if you know or not, I'm not sure, but optical fiber are usually fabricated from silica, which is main form of glass. And as we already know, glass is a transparent material. So from your first impression, you can say that as far as you are fabricating optical fiber from glass, you should not have absorption because glass is a transparent material. It's not an absorptive material. But unfortunately, glass is not a 100% transparent material. Glass has some absorption peaks. The main evidence that you can use to check that glass has these absorption peaks, if you have a very thick layer of glass and just come to have a side view vision for this thick layer, you will find some green color showing in the thickness side of the glass. This green color represents the absorption of the glass at this green peak. That's justify why there is an absorption effect in the optical fiber. Actually, this is typically due to some iron component in the glass. This is somehow some sort of impurities, maybe in the glass fabrication. Of course, the lower the quality of the glass, the higher the absorption. So this is why we have we may have an absorption in the optical fiber, and this is one of the sources that attribute to the attenuation in the optical fiber. Another sources is scattering. I will talk somehow a long time about scattering, maybe after a few seconds. What we call a heterogeneous structure scattering glasses. I mean, instead of having this flat edges in the fabrication of the optical fiber, you have sometimes can have what's called a rough edges, so that's this up and downs. Some textbooks call this surface scattering, due to that the surface is not flat, so you have these triangular shapes in the glass. And also we have what's called the bending. We have micro and macro bending. Also, we have some slides to describe this bending effect. And what's called also splitting. This splitting is whenever you are connecting this optical fiber with another optical fiber or with your terminated device, then sometimes there is some air gap in between, and this air gap, of course, will cause some losses because light will go outside the optical fiber, escape outside the optical fiber. So these are some of the reasons maybe that strongly attribute to the attenuation and just justify why we may have an attenuation effect in the optical fiber. So as I mentioned, glass sometimes or in some frequencies has absorption effect, so that we have absorption. This is a very famous graph to show the attenuation of an optical fiber. So as you can see, this attenuation somehow, in some regions, this attenuation is fluctuating, and in other it's flat. That's why in the optical fiber and maybe in the laser industry, we are searching for the regions at which the attenuation is nearly flat, and we start to work on this region. That's why we have what's called the 3 windows for an optical fiber. We have the first window here between 800 and 900 nanometer. We have the second window here around 130 nanometer, and we have the third window here maybe between 1.5 and 1.6 micrometer, or 1,500 and 1,600 micrometer. Maybe one of the questions that comes in your mind, why we should use this first window as an sending window. You can see that the absorption here is not or cannot be ignored. It's somehow it's high attenuation region with respect to the second window and the third window. But actually, these 3 windows are not only chosen based on the optical fiber industry, but they are also chosen based on the laser industry. Because what you are going to do is that you are going to feed this optical fiber with a light source made of laser. So you have to guarantee that you are capable of fabricating a laser that can emit light in this region. Otherwise, you will not be able to do it. For example, maybe this region is also a flat region, but in this region, for some reason or another, we are not able to have a laser working this region, so it will not be a working region. So you have to match what you can fabricate in terms of a laser industry and what you can guarantee a minimum attenuation in terms of an optical fiber industry. Also, as you can see, this region is a visible infrared region, and these 2 regions are infrared regions. So that's why in many optical communication application, if you come up to the lab and disconnect the optical fiber from the from the N terminal side, from the detector side, and start to see the light going outside the optical fiber, you will see nothing. This is basically because what is inside the optical fiber is an infrared laser source, not a visible light source. So, or a laser source. That's why you cannot see what is going outside the optical fiber. Okay. So the second point is the scattering. As I mentioned, first we discussed the absorption, and now let's go to the scattering effect. What is the scattering effect? Scattering is the collision of the photon with a particle. As we know, light quanta, or the small building unit of light, is photons. If this photon hit a particle, this will cause some shift in its direction. Accordingly, we can distinguish, or we can classify this scattering effect into two main scattering effects. What we call an elastic scattering and what we call an inelastic scattering. For the elastic scattering, whenever your photon is collide with a particle, then the photon direction change within any angle. Let's call it phi scattering, phi s, or whatever. But the photon maintain its energy. I mean, the input photon energy and the output photon energy are the same. So what is changed is just the direction of the photon or the light beam. However, in the inelastic scattering, you have both a change in energy and in phase. That's why we call this an inelastic scattering. Of course, the output energy will be less than the input energy, because in this collision process, you lose energy in a form of photons and energy. So you lose some energy. Accordingly, your energy changes. And basically, if you remember the basic principles of Planck's, saying that the energy of a photon is equals to Planck's constant h times mu, where the mu is the frequency, you can easily understand that due to this process, the frequency of the photon, I mean the light you are transmitting, will be different. You will have an incident light and an going out light, and both are not the same, because basically you change the energy, so you change the frequency of the light, and we call this an inelastic scattering. I believe that during your undergraduate study, you will never deal with inelastic collisions. What we are going to deal with mainly is the elastic collisions or the elastic scattering. By the way, there is another third phenomena where you can increase the energy of the photon, not to decrease. Maybe this appears in what called the plasmonic optical structures. Of course, this is out of focus for this module. Okay, so let's turn to what we are going to go through, which is the elastic scattering. I mean that the energy of the energy is the same before and after collision, but what happened is just that the photon, it changed its direction. We have classified the types of the scattering based on the dimension of the particle you will collide with. As I mentioned previously, scattering is the collision process between photon and particles, or what we call scattering particles, or sometimes we call it scatterers. So this collision between the scatterers, or the photons as the scatterers, or the photon as the scattering particles, can be classified based on the dimension of the scattering particle. And herein, we use the wavelengths of the light as a reference of classification. So if the particle is too small, when I mean the particle is too small, is that this particle is smaller than one order of magnitude of the wavelengths. For example, if I'm transmitting a light which is 550 nanometer wavelengths, then Herein, the scattering particle should be smaller than 55 nanometer, which is lambda times over 10. In this case, what we are going to do is what's called the Rayleigh scattering. We will classify these methods later on, but this is the first category, when the scattering particle is too small. The second is whenever the scattering particle is between lambda over 10 and lambda, so between, for example, 55 nanometers and 550 nanometer. In this case, what we are going to deal with is what's called the mean scattering model. Finally, the third and the final part is whenever the scattering particle is too large, I mean it's greater than lambda, greater than 550 nanometer, for example. In this case, we are dealing with the normal ray optics, or the optical scattering, the normal optical scattering, and this sometimes in the optical is called diffraction. Maybe you hear the word diffraction before, when the light diffract due to an obstacle. So let's focus on the first two categories whenever we have a very small nanoparticle that collide with the optical rays. The first one is the Rayleigh scattering. In the Rayleigh scattering, this is the equation describes the intensity of the light after scattering. And it says that this intensity is proportional to 1 over lambda power 4. So if we return back here using this equation, because this is actually one of the very important natural equation, and I will tell you why this is a natural equation. So let me turn the page. Okay, perfect. So now for the Rayleigh scattering, you have a scattering particle which has a dimension less than lambda over 10. Lights come from this direction, then it will start to scatter. Okay, in different directions. The intensity of scattering is inversely proportional, to lambda power 4. Okay, perfect. So if we reflect this into the spectrum, in the spectrum we have what's called the ultraviolet spectrum, the visible spectrum, and the infrared spectrum. This is the smallest one, which is less than 360 nanometer. And this is in between 360 and 800. And this is larger than 800. So as the intensity is inversely proportional to lambda power 4, that means that lower lambda will have higher scattering than higher lambda, because it's inversely proportional. So whenever lambda is low, the intensity of scattering is high. Whenever lambda is high, the intensity of scattering is low. It's an inversely proportional, it's a strongly inversely proportional function, lambda per 4. So how this equation affects our natural life? Let's see. Okay. This equation actually answers the question why you see the sky blue. Generally, the sun transmits the full spectrum to us. Ultraviolet, blue and violet, reddish, yellow, orange, visible, red, and this infrared. All this spectrum is transmitted from the sun. However, due to the air particle, the atmospheric envelope air particle, a Rayleigh scattering starts to occur. This Rayleigh scattering is inversely proportional to the wavelengths, because the particle of the atmospheric envelope is very, very, very small. I mean, it's less than 10 lambda over 10. That means violet, blue, and light blue will scatter in a very heavy manner. However, the visible and the infrared will be scattered in a less manner. Accordingly, the scattered light will start to appear everywhere, which is the sky, but only the visible and the infrared will relatively transmitted to reach the Earth's ground. And this is why Earth is protected, because as you know, ultraviolet radiations are harmful to the human bodies. So this atmospheric envelope scatters the harmful light with a high scattering, as you can see, and protects the Earth's ground from these ultraviolet radiations. That's why Rayleigh scattering is extremely important. Okay, the other type is the mean scattering model. In the mean scattering model, herein, we have the intensity proportional to lambda, not to lambda power 4. And in this case, as I mentioned, the particle is between lambda over 10 and lambda. This is the second nanoscale scattering, let me say. Okay, let's now turn to the third issue, which is the bending. If you remember, let me back to the this slide. We first discussed the absorption, the scattering, and now let's talk about the bending. As I mentioned, we have two main types of bending. What we call the micro bending or the micro bend, and what we call the macro bend. Usually the micro bend is a fabrication issue. I mean, within the fabrication process of the optical fiber, there is some inhomogeneity or some bending in the core and the cladding, as you can see. This usually can be investigated by testing. Most of the time, this is difficult to be recognized by naked eye, so you have to make some sort of testing and characterization for the optical fiber in order to pick up the region at which there is a micro bending. On the other hand, due to different logistic and dimensions, sometimes we need to make this optical fiber somehow in a curved manner. Not all the time it will be maintained or it will be fixed straight. And this case is what's called the micro bending. Accordingly, of course, as you can see, bending can cause losses because you change the angles or you change the borders, so losses can appear like this and this. Accordingly, there is what's called a critical radius at which you can make your bending on. If you increase this radius more than the critical radius, then losses will start to increase significantly. This equation describes the critical radius. Of course, you are not required to memorize it. This equation is a function in N1, N2, and lambda. And based on the core cladding and the wavelengths you are transmitting, you can determine your critical radius. So this is the macro bending effect. Okay, so now let's go to the other side. As I mentioned, let me return back to this slide. As I mentioned, we have two major impacts while transmitting a signal over an optical fiber. The first major impact is what's called attenuation, or what I describe as that the total energy received is less than the total energy transmitted. And during the previous part of the lecture, we have demonstrated why there is an attenuation in the optical fiber. Now, let's turn to the other phenomena, which is the dispersion. The word dispersion is a very, very important word in the optical field. Dispersion in general means that your signal is not your different signals has not the same velocity inside the optical fiber. What do you mean by different signals? Are we transmitting different signals? The answer is yes. You may ask me, no, we are transmitting only one signal. So for example, this is a dispersion. Now you are transmitting one signal, it's one pulse. Yes, but inside these pulse, you have different frequencies. As you know, this rectangular rect function results with a sinc function in the frequency domain. That's why we have a different frequencies. And each frequency will propagate inside the optical fiber with different velocity. Again, each frequency will propagate inside the optical fiber with different velocity. That's why whenever you have this high sharp edges, which is the indication for high frequency component, and you transmit your signal over an optical fiber, you have a smoothed output. This is due to the low pass filter effect. If you remember, we say that the optical fiber is a low pass filter system. And the other phenomena is if you have an input of which, let's call this T capital, which is the width of the particle of the pulse here, the output pulse will have a width, let me call it T dash, where T dash is greater than T. This is the dispersion effect. But why dispersion is harmful? The answer is here. If you are transmitting two successive bits or symbols together, due to this dispersion effect, these two symbols can overlap together. And in this case, you are not able to detect the signal on the receiver side. This phenomena is called in the communications the intersymbol interference. So intersymbol interference can happen in optical fiber due to the dispersion effect. In order to fix or maybe isolate the signal from this intersymbol interference, we have to reduce our bit rate. So instead of transmitting data, for example, with 1 over tau, where tau is the width of the signal, then you can transmit it with 1 over 2 tau. So we have a space tau between each two symbol and its neighbor. This is called the guard band in the communication. So you can have this guard band between each symbol and the other. And then whenever you have a dispersion, you can ensure that no intersymbol interference occurs. Or sometimes we use such an empirical formula. We say that PT, or the bit rate, or the symbol rate, of course, is equals to 0.2 over sigma, where sigma called the RMS light pulse at the output of the fiber. As I mentioned in the beginning of the lecture, in this lecture you will find a lot of empirical formulas that is used directly in the industry, because usually in industry you are not going to make a lot of hypotheses and theories and so all this stuff. You need just to calculate using a very simple one direct substitution equations. So this is one of the equations, and actually we will talk somehow about sigma by the end of this lecture. So the main, or not the main, the first reason for a dispersion is changing in the frequency, or what we call the chromatic dispersion. If you remember the word chromatic, we use it in the zero lecture when I described to you the behavior of a laser, and I told you that laser is a monochromatic source. So chrome is light, or is color or frequency. So due to the monochromatic sources, you have dispersion. And one genius student can stop me now and told me there is a big conflict in what you are saying. You said that lasers are monochromatic sources. And you said also that optical fiber are fed with lasers. So why we should have a chromatic dispersion in lasers? The answer is very simple. Nothing in life is identical. Nothing in life is ideal. There is a purely monochromatic source ever. Any laser source will have some sort of bandwidth, a dyschromatic behavior. It's not a monochromatic behavior. You have a range of frequencies, not a pure delta Dirac function. This maybe will illustrate it later on whenever we go to the laser chapter and describe how the spectrum, or the frequency response, for a laser looks like. So generally, you will never have a purely monochromatic laser, and accordingly, you can have a chromatic dispersion due to the non-ideality of the laser. So again, having different light colors, different frequencies, each frequency have a different speed. As you can see, for example, the blue one is the fastest, and the reddish is the slowest. So these frequencies, or these light beams, or these frequency components, has different velocities inside the optical fiber. That's why we have this chromatic dispersion. Now the question is, why we have different light source, why we have different different velocities for different frequencies? What is the reason for that? Why not we have all light propagating with the same velocity? Okay, let's try to answer this. This is actually very important. So, from your microwave electromagnetic classes, you know that whenever we have a medium, electromagnetic waves propagate on this medium with the velocities v, where v equals to c over root epsilon r. I think you already see this equation before. C is the velocity of light, which is the velocity at which light propagate in air. But whenever you have an epsilon r, I mean epsilon r is not equal 1, which is the air case. Whenever you have an epsilon r, then you should predict or expect a reduction in the speed with a factor root epsilon r. And as we mentioned, this root epsilon r is equals to n. Okay, but from the first principle, this is not a reason for different velocities for different frequencies. But what if this n is function in frequency, or in optics we call it usually mu, not f? If n, which is the case, is function in mu, then each frequency component will have different velocity with respect to the other. The variation of the refractive index with frequency, called the dispersion effect of the material. If you remember, some slides ago, I wrote to you this equation. N equal N dash, or N real, minus JK. And I told you that K is the term responsible for absorption. Now, let me tell you that N is a term responsible for dispersion. Whenever, of course, N is a function in mu. And this is happen everywhere. Sometimes you can neglect it. Whenever you are young in your physics class, we told you, for example, that the refractive index of silicon is 3.9. It's a constant. Of course, this is an approximation. Realistically, N is all the time function in frequency. And this is a dispersion effect. Accordingly, this very simple equation turns to be in this format. So this is the general form for calculating the velocity of the wave inside an optical fiber. C is the same, N, which is root epsilon r as usual, but now we have a new term to describe the dispersion, which is lambda dn by d lambda. Of course, dn by d lambda can exist whenever n is function in lambda, or I mean n is function in mu, because of course if n is function lambda, it will be automatically function in mu. So if n is constant, this term will tends to 0, and then you will have the familiar version of the equation, which is c over n, or c over root epsilon r. And we call this denominator, which is n1 minus lambda dn1 by d lambda, as ng, or the group refractive index. The group refractive index include the dispersion effect inside. This is, as you can see, this is a dispersion effect in a material whenever the refractive index is function in wavelengths. This is, for example, for silicon. Another important point, here we are considering N1, which is the core material, because this is the material where the light is propagating. That's why we are interested in we are not interested in the cladding material because no light propagates in the cladding material. Accordingly, you can determine the time taken for a signal to pass inside an optical fiber, because this term represents the velocity, and this term represents and of course the length of the optical fiber. Let's say this is L capital, so L over C can determine the total time of the total time taken to have the signal, which is L over C n1 minus lambda dn1 by dt. And again, you can see that the dispersion is affecting the total time of delivery. Finally, we have this M term. This M term represents 1 over speed. As you can see, it's time over length. So is some sort of an mathematical variable used to describe the optical fiber. It's called 1 over L d tau by d lambda. And this M term can be implemented very easy by having the first derivative of this equation and then divide by L. So this L will be cancelled by this. And herein, we should have actually two terms. The first is the first derivative of N, and the second is the second derivative of N. But usually, the second derivative of N is dominant with respect to the first derivative. That's why we ignore this first derivative of N. Of course, this is actually somehow a complicated differentiation equation, because you have here lambda dn by d lambda. So what you are going to do is that you first differentiate the first, which is lambda, and keep the second constant, which is dn1 by d lambda. Then this will cancel with dn by d lambda, and then we will have this. Let's make it step by step to make it easier for you. So let's make it step by step. We have the term tau, which is equals to L over C n1 minus lambda dn1 by d lambda. And we introduce the term M as 1 over L, it's a normalized term, d tau by d lambda. So this is a normalized term, and actually this is one of the advantages of M, by the way, because as you can see, T, or the time taken for propagation, is directly depend on the length of the optical fiber, which is of course a variable parameter from one optical fiber to another. However, this M parameter is a normalized. However, this M parameter is a normalized parameter. So this M is a data sheet parameter for an optical fiber, because you can normalize over L, and then this is a standard for any optical fiber. So now what we are going to do is this L will be cancelled with this L, and then we have we have 1 over C. Then let's start the differentiation. First we have these differentiations, then it's dn1 by d lambda minus. Then let's first differentiate lambda, which is 1 minus dn1 by d lambda. Then we have the second differentiation, which is again minus dn1, sorry, minus the second derivative of dn1 by d lambda square. And here we still have the lambda, which is the second. So this term is cancelled with this term, and then we have the term lambda over C in the second derivative of N with respect to lambda. So this is the second derivative of the refractive index whose term is lambda, and this results with M as a fabrication parameter for an optical fiber. So you can know M whenever you can access the data sheet for an optical fiber. So why this M is important? If you remember the term, sigma in the beginning of this lecture, let me show it to you. Okay, so this sigma, if you remember, which, as I mentioned, an empirical formula used in order to describe the maximum bit rate that can be conducted in an optical fiber, O(2) over sigma. And I told you that we will describe, or we will demonstrate sigma later on. So this sigma can now be calculated by using sigma equals to sigma lambda, which is the width for a single wavelength, times by L times by W. Sigma lambda is usually a source dependent, so you can know it from your optical source. L is the length of the optical fiber, and M is the normalized parameter that describe the propagation in an optical fiber. So if you multiply these three terms, you will get sigma M, and then you can substitute in this equation to know the maximum data rate used in order to transmit your signal. Again, these are all empirical formulas used in order to demonstrate the optical characteristics of an optical fiber. Now, we finished the first kind, or the first type of dispersion effect, which is a chromatic dispersion. I mean, this dispersion is due to different frequency component of the source. But is the chromatic dispersion is the only source of dispersion on optical fiber? The answer is no. We have another famous dispersion effect, which is the multipath dispersion. Generally, dispersion means to have different velocities of propagation, which is the case in the chromatic effect, dispersion, because each chromatic line, each frequency component has its different speed or velocity. Now, if your optical fiber accept different passes of light, I mean, you insert a light signal. Some of these light signal will propagate directly in a straight line, like this one. However, the other will propagate in this triangular form. So you have a faster version and a slower version, a faster mode and a slower mode. Of course, this can happen especially when you are working in a multi-mode optical fiber. In this case, you should expect dispersion. But how we can eliminate this dispersion? Of course, the solution is very easy, is to have the smaller radius possible. And thus can result automatically if I pick up two different optical fibers, one with radius X and the other with radius Y. And I told you which one of these two optical fibers has higher dispersion effect. Your answer will be directly with the greater, the larger one. The larger radius, the larger multipath dispersion effect. So you can generally control this multipath dispersion effect by controlling the radius. However, this introduces a trade-off between the number of modes and the dispersion. Of course, in order to transmit more and more data, you need to have a larger radius, because if you remember early in this lecture, we have an equation for the number of modes, I think. Yes. Yeah, here it is. Yeah, this equation is for the number of modes. And as you can see, the number of modes is directly proportional to A, where A is the radius of the optical fiber. So makes sense. The larger the radius, the larger the number of modes. But herein, you have a trade-off, because whenever you increase the number of modes, you will decrease, you will increase also the bit rate. So you are going to decrease the, you increase the dispersion, I'm sorry. So you are going to decrease the bit rate to eliminate or to reduce the multipath dispersion. So it's a trade-off between increasing the number of modes and increasing the dispersion, which is, of course, a negative sign that limit the data rate in an optical fiber. Now, this is the termination for lecture number 1, dealing with optical fiber communication. In this lecture, we have studied together, first, the overall construction of an optical fiber from a cool and clay material, different types, including step and graded index. Then we have discussed together the main major impacts of an optical fiber in terms of attenuation and dispersion, either chromatic or multipath dispersion. This is the termination of lecture number 1. In the next lecture, we are going to go more toward communication. We are going to deal with optical modulation and optical demodulation in optical communication system. So see you later on in the next lecture, and please enjoy your weekend. Bye bye.